Okay, so let's talk about the notion of a face. All right, so this is a new structure that's going to be an additional sort of piece that comes with vertices and edges. And what happens is a face is not something you have until your graph is embedded. All right, so let's talk. A face is a region formed after embedding a graph on a surface. All right, now we have on a sphere you have the luxury of everything, every region that you form is a face. So let me go ahead and note this. This is pretty special to a sphere. So on a sphere, every embedding of a connected graph, it's important that the graph is connected. So let me make sure the sentence makes sense. On a sphere, every embedding of a connected graph, oops, I'm missing a word, divides the sphere into faces, edges, and vertices. Okay, you can think of these as three building blocks to build a surface. Okay, so you can think about if you were to, think about this being hollow, right? The red dots would be sort of the vertices, the gluing points where edges are connected to one another, and then the faces are glued to one another via the edges. Okay. All right. On other surfaces, you don't get this notion of a face quite as for free. It does come for free on a sphere as long as the graph is connected, but on a torus or other surfaces that are complicated, things could go awry. So, what do you need? Okay. So it's a region formed after embedding a graph on a surface. However, not all regions are faces. Okay. So a region is a face if the following. So the idea is it needs to be if it is what's called simply connected. All right, so this is an old word that kind of got readapted to a more modern context later on, and we kept the word simply connected. Having an intuition of what this means is actually not that difficult to grasp. So, some things that are simply connected. Alright, if I take a disk, this is a surface with boundary, this is simply connected. A sphere is simply connected. Oops, sorry, my marker slipped out of my hand. That's simply connected. Three-dimensional space. The whole thing, so R3 entirely. That's simply connected. All right, and then there's probably a lot of other sillier examples, but these are good ones. Okay, some things that are not is if I have a disk with a hole in it. And this is where the old naming scheme came from. This was simply connected, and then this was often referred to as multiply connected. And the terminology was sort of came from historically was looking at how many pieces of boundary it has. So this has one boundary piece. This one has two boundary pieces. So in the plane, that was a nice way of detecting whether things were simply connected or not, was to look at how many boundary pieces you have. However, this is specific to the plane or the sphere to look at boundary pieces. If you end up on a torus or something, this doesn't work. Let's see, something else that's not simply connected, a coffee cup, or a donut, right, or a rubber band. And you can probably start finding some similarities here, right? These all sort of have these loop structures in them, right? The coffee cup is a handle, donut has this thing. This thing is not simply connected. Here. Anything with a loop is not simply connected. Okay? Alright, so now what does it mean to be simply connected? Alright, well, it means you can put in a loop and you can do something called homotope it to a point. Really that means you can put in a rubber band, so you have to excuse the rubber band, but I like to point it out. Put in a rubber band and it can what's called retract or homotope to a single point. So it can kind of like snap back to a single point. And you can do this on a sphere too. You put a rubber band somewhere on it, be as creative as you want, but you can always snap it back to a point. And there are some cool consequences of this. That it turns out that the process of the homotopy does create this neat disk. But anyway, but you have these explorers out there, right? You can always explore with rubber bands. If it turns out one gets stuck and can't come back to itself, then the region's not simply connected. So this one, if I do a rubber band like this, right, that would discover that it's not simply connected. However, I could put a rubber band like this, right? It would not know, it would not detect the failure of being simply connected, right? So you have to actually put it on the right to detect it. The coffee cup, right, you just do one through the handle. Usually I bring a coffee cup, but I don't have one with me right now. On the donut, just go around the donut just like that. And the rubber band, just follow the rubber band with your rubber band, right? And you can't get it closed. All right, so that's what's important about a face, is a face needs to be simply connected. If you're just working on a piece of plane, you don't have to be so sophisticated. You can just look at the number of boundary pieces. So if you're on a plane, if it has one boundary piece, then you're good. But when we start working on like a torus, or if you want to get creative and take this material further, you need this notion of simple connectivity. All right, so you do have to embed your graph first before you can start messing with faces. If you're embedding your graph on a sphere, and your graph is connected, then you're good. Everything there is a face. If you take your graph and you embed it on a torus, you may have embedded it in such a way that many of the regions are faces, but some are not. Okay, so keep in mind that that is possible to do if you embed it in such a way that leaves you with something like a handle left behind. Okay, so we have to do some practice with this. We're going to have to work with what different embeddings look like. And we're going to start with the sphere, so we're not going to get ourselves in much hot water for quite a while. But once we start doing embeddings on the torus, then we'll have to take a look at what's going on there. And sometimes, keep in mind, we're not always going to take this perspective of a graph and then putting it on a surface. Sometimes it's really helpful to switch your thinking and think about, okay, take the surface and then decompose it into vertices, edges, and faces, right? So I like take this, think of it this way, I had this blank styrofoam sphere and I drew a graph on it. I decomposed it into constituent pieces. Okay, and that perspective is kind of neat, right? Because then it makes it feel like the surface is still the surface, and it just you can draw certain things on it, but it's built out of pieces, right? Okay, and then like this, this one's hard to see, especially in camera. But you can do this with a torus as well. You can see this one was built in pieces. If you just ignore the yarn that was there for a different purpose, you can see it has these faces. They're different colors. You can see the color separation is by the yarn, but right, this was sort of built from faces, vertices, and edges. So, okay. So the next one we're going to do is do some work with this. We'll start actually playing some games with accounting for edges, vertices, edges, and faces, and we'll take it from there. All right, so I'll see you in the next one.